to understand the concept of observable canonical form, let us look at this example. So the problem statement is obtain the state model in observable canonical form of the transfer function which is given by y of s by u of s is equal to s square plus 2s plus 1 divided by s cube plus 4s square plus 5s plus 6. So for this transfer function, we need to obtain the state model in observable canonical form. Controllable canonical form, observable canonical form, these two some of the standard forms where we can represent the transfer function in the state model. So in observable canonical form, the given transfer function must be rewritten such a way that we can easily draw the signal flow graph using the Mason's gain formula. So for that, let us look at the denominator. The highest degree is 3. Therefore, we can take s cube here common the denominator. Similarly, in the numerator, then I can change the transfer function. The transfer function is going to become y of s by u of s is equal to, we have 1 by s plus 2 by s square plus 1 by s cube divided by, anyway we have taken s cube common, therefore 1 plus 4 by s plus, then I have 5 by s square plus 6 by s cube. Again the denominator, I am going to change it as numerator as it is. The denominator, it is a 1 minus inside the bracket minus 4 by s minus 5 by s square and minus 6 by s cube. Now this transfer function is in the form of Mason's gain formula, where the numerator terms gives us the forward paths and the denominator terms give us the individual loops. Now the basic assumption in this is we have individual loops, those all loops are touching each other. There are no non-touching pairs. And the other assumption is all my data values delta 1, delta 2, delta 3 are is equal to 1. So with that assumption, then I can draw the signal flow graph for this transfer function. Now what are the forward paths? We know the forward path, 3 forward paths we have. Before going to take the forward path, let us take integrators. How many integrators we need to take, it depends on what is the order of the system. The order of the system is 3, therefore I need to take 3 integrators. Now look at, I am taking 3 integrators like this, 1 by s, 1 by s, 1 by s. Then for each integrator, the output of the integrator is state variable, input to it is a derivative of the state variable. Now in state model, using signal flow graph, when you are obtaining, I am going to take in this fashion, means I will take the first integrator output is x1, next is x2, next is x3. So we can also take in the reverse direction, you will get a different ABCD matrices. As we know that state model is not unique, so we will be getting a different models by taking different state variables. Now this is x1 and this is x1 dot, and this is x2 and x2 dot, and x3 and x3 dot, and the output variable y and input variable is u. Now I want to take forward paths, so we can take the forward path, the first forward path from u to directly x3 dot node, and from that we can go to up to y, so that becomes 1 by s. Then I can take one more forward path, start from u, and I can go to x2 dot, and I can go straight to the y. So this becomes my 2 by s square. Similarly, I can have a straight from u to y, one straight line, which is one more forward path, which gives us 1 by s cube. So 3 forward paths are always drawn from the input node. We have to start from the input node, then we can take all the forward paths. Similarly, I can take the output node, then I can draw all my individual loops. Okay, so while taking the loops, anyway you have minus, that minus should be take care. So the first one is minus 4 to the x2 dot, and I have again minus 5 and minus 6. So when you look at a loop such that it should get, the first loop is 4 by s, and second loop is 5 by s square, and the third loop is 6 by s cube, where we have all minus values. So this way we can draw the signal flow graph. Once your signal flow graph is ready, then we can write the equations for the derivative of the state variables. And what are the derivatives? x1 dot, x2 dot, x3 dot. So when you write equations, and those equations are goes like this, the first of all we'll write the output equation. The output equation is nothing but, so we have x1, and from this x1 we can write x3. Directly we can write y is equal to x3 because output variable is y and before that we have x3, last state variable. So y is x3. Then what are the state variables? We can write the state variables. X1 dot is u minus 6y. So wherever y is there, I can substitute with x3. So that is going to be x1 dot is nothing but u minus 6x3. Similarly, we can write x2 also. We can write because x1 we have already. There are three incoming branches. For that, whenever you write equation, you should look at only incoming branches. So x2 dot is nothing but x1 plus we have y and we have x3. So with this we can easily write the equation, and when you write the equation you will get the next equation number. Then similarly x3 dot, so we can also look at the x3 dot, and x3 dot is nothing but x2 dot plus u minus 4y. So with this I can substitute in place of y x3 again and I can get the equation. So when you take the equations and when you put in the matrix form, you will get the state equation. The state equation looks like this: x1 dot, x2 dot, x3 dot or derivative of state variable is equal to, we have A matrix, and what are the entries of A matrix? I have 0, 0, minus 6. With the help of the equations you can entry, and your second row is 1, 0, minus 1, and I have 0, 1, minus 4. These are the entries of my A matrix. It is 3 by 3 matrix. Similarly, we can also get the B matrix as 1, 2, 1. So these 1, 2, 1 are the numerators in fact, and the last column of A matrix are the denominator coefficients. So y equation also you can write down from the first equation, because y is equal to x3, then that will be 0, 0, 1 is C matrix, anyway D is 0. D is 0 because number of poles of the transfer function are greater than number of zeros. If at all, if your number of poles is equal to number of zeros, then you will get D as some value. But in this case it is going to be 0 because it is a proper transfer function. So this way we can obtain the state model, and we know that if observable canonical form is available, then we can easily get the controllable canonical form, either because they are dual each other. So these two, observable canonical form and controllable canonical form, are also called bush forms or companion forms. So there are different names to them. Now, what are the advantages of phase variables? So phase variables, using the phase variables directly we can find out the controllability and observability of the system, which is very important in state space analysis. So directly in controllable canonical form, we can easily say system is controllable or not. From OCF form, we can easily say the system is observable or not. So this is one of the very important advantage. Similarly, we can have the relation between the time domain as well as the transfer function domain. So we can easily get the relation. So we can also obtain the state of the system very easily using the phase variables. But what are the drawbacks of the phase variables? The drawbacks is the phase variables are not the physical variables. Let us take when you have RLC system, the inductor current, voltage across the capacitor are the physical variables. But in phase variables, we are not going to take those as the state variables. In OCF form as well as in the CCF form, we are not taking the current, inductor or capacitor voltage are not state variables, which means so all the phase variables may not be physical variables. If they are not physical variables, we cannot measure them. So when they are not measurable, again what we can say is the next point, the design of the controller becomes very difficult whenever you have the state model in controllable canonical form or observable canonical form, which usually called as a phase variable form.